All right, so let me start. So today's speaker is Arif Ullah. He is one of co-organizers, and it was basically very brave from him to be the first because this is a new scene and not very well established. So I will try to explain first what is SMLQC and what is our vision behind it. So first of all, it is dedicated to machine learning and quantum chemistry, but we also see now that many new interesting developments are in quantum computing, where machine learning is actually also playing a big role. There are algorithms for machine learning on quantum computers, and that is now increasingly applied to quantum chemistry. That's why we kind of extended this topic to very broad ones, also inspired by our SACAM workshop, which we organized recently. Yulia was also co-organizer, and she's here. And that's why back then we already saw that this is becoming something we need to include. The main difference from other usual seminars, online seminars, is that we don't just provide online lectures. We actually do requests from speakers to also provide hands-on experience for participants so that they can actually learn from it. So it's kind of a short schools, and then it's spread over the year, so there is no break, and then you can learn from these tutorials. And that's why we want to invite people who do this research, who actually write the code, who know the code. So they are typically young researchers, postdocs, and PhDs. And we will see, like in the future, also many new people who give excellent research and basically who have nice results that we can read and we're interested in. And since we have Slack platform, so there we can also exchange some interesting papers that we may want to learn more about and check the code, so we can invite people from these papers too. So more information on this website, which you can see here, and you can check it there. We also update it on information on Facebook and Twitter, so the links to the social media platforms are also on this website. We also basically use these seminars to bridge big SMLQC Symposia, which is biannual event hosted in different regions. So the first one was in 2021. It was hosted in Xiamen, although it was virtual event due to COVID. Now, in this year, we'll have it in Uppsala, in Sweden. We started basically, Roland Lind started to organize it already, and we had some exchange. So more news will come later. Please subscribe to our channels, and then you will be notified in time when we have some news about this big symposium. Now, as for organizers, so this is me here, and Yulia, you also can see online, so she will also introduce Arif, who is also is the first speaker, and we also have Max Pineiro Jr., who suggested many good ideas for these tutorials. Basically, he was the one who was suggesting the hands-on part of it, so that's up to him. And Alexey Kononenko is also one of our co-organizers. So you will learn. So we also have new members coming because we want to cover many different areas of research, and machine learning and quantum chemistry is very, very broad. Right? And we also have many different regions, so we want also to have diverse coverage of the whole world. Now, as for the speaker, Yulia will introduce. So here, I will just tell the next, we also have already scheduled for the next speakers. And there is Max Pineiro Jr., also Pascal Friedrich from Karlsruhe Institute of Technology, Daniel Schwalbe-Koda, and Johannes Margraf. Many of these names probably you know because you can find them in many good papers. All right, so I will just give it to Julia, and she will introduce our first speaker, who is Arif Ullah.
Okay, thanks for introducing SMLQC, and I'm very happy to be on the organizers team and to introduce the first speaker, Arif Ullah. He was born in 1989 and has completed his bachelor and master degree in physics in Pakistan. In 2015, he then joined Professor Yin Yan groups at the University of Science and Technology of China, and he completed his PhD in 2019. In 2020, he then went to Shanghai, New York University for 1 year postdoc, and later in 2021, he joined Pablo Dral at Xiamen University. And since then, he's working on the development on machine-learned-based quantum dynamics approaches. And today we have invited him to give a talk about his recent work. And it will be followed by a tutorial that will demonstrate how to perform machine learning-based quantum dissipative dynamics with the MLQD package. So Arif, the stage is yours.
Thank you, Julia, for the nice introduction. So let me first share my screen. Okay, so I hope you see my screen. So the topic of my talk is quantum dissipative dynamics with machine learning. So let me first introduce what is open quantum system. And so in reality, there is no isolated system. So every system, it has some environment, it always interacts with it. It exchanges particles and also energy, pays with it, with the environment. And then in the equilibrium established when like there are fluctuation, there's some dissipation, and there's equilibrium established after some passage of time when these fluctuations are equal to dissipation. And the most classical example of open quantum, not open quantum system, but open system is the Brownian motion, which was discovered by Robert Brown in 1827. Though Brownian motion is a classical system, open system, but here we are interested in quantum systems. So I will just talk about open quantum systems. So usually the Schrödinger equation we see in our undergrad books is actually for isolated system. So we don't consider any environment there. But in reality, there is no isolated system. So we need to consider the surrounding environment. Even if we, like in our experiment, when we perform some measurements and even when we do some observation, our measurement device is also counted as environment. So it's also like we need to consider the effects of those measurements and the measurement device on the system dynamics. So to do that, we need to add some extra terms to the Schrödinger equation here. So here, let me change it to the pointer. Okay. So here we need to add some extra terms which counts for the surrounding effects. Here, why we want to study open quantum system. So I will just give you a few examples. If like in solvents, if there is an electrons transfer between molecules, you need to consider the solvent effects. So your solvent is an environment. Similarly, the light harvesting processes where the light passes from antenna to the reaction center. There you have protein environments where the chromopores interact with it. And similarly, we have like in quantum computing and quantum information, we have this qubit where it interacts with the thermal environment, and we call the thermal environment noise. So what happens when a system interacts with this environment? So first thing is the dissipation and exchange of particles. So you already know the grand canonical ensemble, if you remember your lessons from the statistical mechanics, is that in grand canonical ensemble, the system can exchange the particles in energy with it. So the energy is not conserved, the number of particles is not conserved. So we need to consider that also the loss of coherence. So the loss of coherence is actually the collapse of the system state. So I will give you a simple example. If you consider the Schrodinger cage, so before observation, it's in a superposition of two states, like the cat may be alive, cat may be dead. So when you do the observation, so the system collapses to a single state, you find out that the cat is in one state, it's dead or it's alive. So you lose the loss of coherence, and this loss of coherence is the biggest problem in quantum computing, because we have these noisy quantum computer, and when because of the noise, we lose this coherence, and when we do some measurements on the qubits, it's also collapse the state. So after each measurement, you need to rebuild the state. So it's not like you can do measurements again and again on the same state. So there's also a big problem in a downside of the quantum computing. So methods, to talk about methods is, there are some full quantum methods, there are some quasi-classical methods, and there are some fully classical methods, like if you want to study the open quantum system. So in full quantum methods, what we call full quantum methods. In full quantum methods means that we study the system and the environment both quantum mechanically. In quasi-classical methods, because the environment is so large and it's hard to deal with it, so what people do is they replace this, they deal with the environment classically in the system quantum mechanically, so we call it quasi-classical methods. But there are also some methods where they deal the system and the environment both classically. So I will give you a few examples of all of these methods. So in these full quantum methods, I will give you a few examples like the HUM method, the stochastic equation of motion method, the QAPI. These are a few very famous methods in this era, in this area. And this similarly in the quasi-classical method is surface hopping, linearized semi-classical method, and in the polyclassical, this Mayer-Miller MM mapping. In this chapter, we in detail discussed the full quantum method and the quasi-classical method, but you can have a look in this chapter. What are the challenges? So the challenge is about, like, in this classical and quasi-classical methods, the problem is because you deal with the environment classically, so you lose some quantum features like the coherence and zero-point energy. There are, like, people also do some, like, use some techniques to aid these features to the dynamics, but still, like in some cases, in strong quantum regimes, it still, like, fails. But the full quantum methods, they are like, they are exact numerically, but the problem is they're quite expensive and numerically challenging. So to give you an example about the numerical challenges for this full quantum method, I will give you an example about, let's suppose you consider the stochastic equation of motion method. It has a very bad convergence in the long time regime, and here in this plot you can see that in this long time regime it has a very bad convergence. So if you want good convergence in this a long time regime, you need to generate millions of trajectory and take average over it. So it's quite expensive. Another method is this HUM method, which is quite famous. It has this huge memory problem. At low temperatures, you need huge memories. Even like, recently we were doing some calculations, even 1 terabyte memory was not enough for it, for some calculations. So it's quite expensive memory-wise. So how about machine learning? Because machine learning is about how to do fast calculations and decreasing the computational cost. So how about if we use machine learning in this area? And the good points about machine learning is it can find correlation inside the data without any physical laws. And similarly, the computational cost of machine learning based methods does not depend on any parameters. So it does not change with temperature or any other parameters. And similarly, machine learning is fast, so we can minimize the computational cost. So the example that I just showed you in the last slide is here, this method where we have this, like in the long time regime, we have very bad convergence. So one can think about it like if we provide this short time dynamics as an input, and then let the machine learning predict this long time dynamics. So we did this study recently, like in 2021, we published it, and we performed this study for a 2-level system. We call it spin boson model. And this is the Hamiltonian for that system. Here we have these are the different parameters for it. So the 2-level system can describe for you a qubit, like you have up and down. So it's a 2-level system for you. You have product and reactor, and it can be a 2-state system. A dimer is a 2-state system, and other system like, so a 2-state system can describe many processes in quantum mechanics. So we used a kernel ridge regression, which is implemented in this MLATOM package. You can visit MLATOM.com. And here, what we do is we provide some parameters like temperature, system bath coupling, and other parameters in traditional method. And then we generate a short time trajectory. And then we provide this short time trajectory to our trained machine learning model, and then it predicts the long time dynamics for it. So the results I'm showing you here, these are results for unseen trajectories. So what we do is we provide some unseen parameters to the system and generate a short time dynamics and then provide it to the machine learning model. So here you can see it. In our results, what we found very interestingly is that it was not only able to interpolate, it was even could extrapolate beyond the training regime. Like we trained this model only up to t equal to 20. So here up to this time, but it was able to extrapolate beyond it. So the results I'm showing you here beyond 20, it's like extrapolating. So it's still like it could learn the behavior and it do the extrapolation. It still like knows how to. So it was really amazing about it. But okay, as you know, there are like many machine learning models. So we call it a zoo of machine learning models. So there are neural networks and there are kernel methods. So there can be a question like which method, which model can perform better. So recently we performed a comparative study for it. So we considered 22 models, 14 of them were neural network models and 8 of them were kernel models. And these plots or results here, you can see that the kernel models, they outperform neural network model, all of them. And like on training time wise or prediction time, like in error wise, like they all like kernel methods, they just outperform neural network models. So here you can see that the mean absolute error for kernel methods is quite low as compared to the neural network models. The training time is quite low as compared to the neural network models, and the prediction time is quite like, you know, fast as compared to the neural network model. So it was like quite amazing. And but this study was only performed for two-level system, so we cannot claim it for maybe if the system is large. So it may be not true, because the kernel methods, they have their own challenges, and like because of the computational costs. So, but there is a challenge. What I showed you, the study that where we provide a short-time trajectory and that predict the long-time dynamics. The problem with this approach is it's recursive, and because of this recursive nature, it may accumulate error. Like here, if you provide a short-time trajectory here, it predicts the next time step. And what we do is we include this predicted time step in our input, and then we provide it again to our machine learning model, and it predicts the next time step for us. And then we again include the time step in our input, and then again provide it to machine learning models. So if something goes wrong in these time steps, then your next prediction will be like it will have more error. So it will diverge. So this is, we call it accumulation of errors. So this can be a problem in this approach. The second point is it needs a short-time trajectories and inputs. So still, this machine learning method is not quite independent. You still need those traditional methods to get short-time trajectory and then use machine learning. So what we did is we proposed another approach. We call it AIQD. What we wanted is we wanted to remove this recursiveness. And another point we wanted is we want to make a very independent approach. We wanted not to have any dependence on these traditional models. So we just wanted to provide the parameters directly to the machine learning, and it could predict the dynamics for us. So the approach we proposed is, the positive points of this approach is here each time step is independent from each other, and it's because we include time in our input. So you provide the time in the input, it predicts the corresponding dynamics for you. So each time step is independent from each other, and there is no sequence. Like you can predict any time, like forward and back. So they're completely independent from each other. And because of this completely independence, you can do parallel computation. And so it can decrease the computational cost for you. And the best thing is about this approach is you can predict the asymptotic behavior without propagation of dynamics. Let's suppose if I want to know the system state at t equal to 10 picosecond, I don't need to propagate the dynamics up to the 10 picosecond. I can just provide my time, the 10 equal to 10 picosecond, and it will just directly give me the state of the system at t equal to 10 picoseconds. So that was a good thing about this approach. And another point is it does not need any short-term trajectory. You just need to provide your initial conditions, you can call it, or your simulation parameters in input. That's it. So here, I will just show you here, like, let's suppose these are our parameters, like these lambda, gamma, temperature. And this is my time. So if it's a logistic function, I will just explain it later why I want to use it. So what you do is if I say predict the dynamics per t equal to 0, so this machine learning model can predict for us the corresponding time. And I just need to change the time only, and it will just predict the dynamics for us. So each time step is independent from each other. You can see it from here. So we applied this approach to exciton energy transfer or excitation energy transfer in FMO complex, which is quite famous. Usually people use it to test their methods. So in FMO complex, we have antenna, and then it's actually a trimer here, but I will just show you a single monomer here. So you have these chromophores, 7, and some studies it's 8 chromophores, and then the excitons, it's created an antenna, and then it transferred to these chromophores, and then it transferred from jump from one chromophore to another chromophore, and then it goes to the reaction center. So the efficiency of this FMO trimer is quite high, and that's why it's quite interesting for the research community to understand how we can mimic this behavior in our artificial photovoltaic devices. So this is our Hamiltonian here. We have system Hamiltonian, and then we have environment Hamiltonian. We consider our environment is a independent harmonic oscillators. You can see here, and then we have this system environment, a Hamiltonian which describes the system environment interaction, and then we have this reorganization term which is renormalized temperature, the Hamiltonian. So here we are just showing if you provide these simulation parameters to the convolutional neural network, it can predict for you the dynamics here. So these are the results. I will just here, these are some technical points. Before training, we choose our trajectories on participant samplings. And similarly, we choose our time length of each trajectory based on this gradient vanishing scheme. And then we normalize our time dimension using this logistic functions here, A, B, C. These are constants. So here, the results I'm showing you, this is the population of sites. So you can see the exciton transfer to site 1, and then it transferred to different sites, different chromophores, and then here, so the site 3 is increasing because it's close to the reaction center, and then from site 3 it transferred to the reaction center. So the whole, like, the excitation is transferred to this last one, site 3, and this is the coherence term. So in mathematical terms, these are the diagonal terms of the density matrix, and these are the off diagonal terms of the density matrix. Another approach we recently proposed, which is quite fast, is the one-shot trajectory learning approach. Is that we thought about, like, what we do, what people usually do, and what we did in this AIQD and other methods, is that people just predict a single time step at a time. So you run your machine learning model and again, like you are running the whole factory for again and again for a single product. So what we thought about is we can predict the whole dynamics in parallel, like in one shot. So which makes the dynamics prediction quite fast. So in this method is quite fast because of this parallel prediction, and it could predict the 10 picosecond long dynamics in only 70 milliseconds. So this kind of approach is quite good for if you're doing some massive kind of simulation and parameters, like if you're doing millions of calculations. So this approach is quite good for massive simulation. So these are the same results. We applied this method to the same FMO complex, and these are the results. And the results I'm showing you these are for unseen simulation parameters. So the parameters like temperature, the system environment coupling, the reorganization energy, these were not like in the training data, it will completely unseen to the model. So here I will just, so what I presented like is for quantum dissipative dynamics. So what people usually also do in chemistry, they don't call it quantum dissipative dynamics, but it's dissipative dynamics. But it's just, in physics, people use different terms, in chemistry, people use different terms. By the way, it's just the same thing. So here, like if you do this in atomistic, artificial, like atomistic calculations, is you know that molecules, they are not stationary, so they always jiggles. And to do this dynamics, to find these coordinates X, Y, Z of each atom, people use these, propagate these Newtonian mechanics in this classical kind of methods. So what you do is you predict the position of the atoms, each atom at each time tip. And for fast dynamics, what you do is you can use these machine learning potentials, and then from these machine learning potentials, you can get the forces and energies, and then you put the energy, and then you can get the force, and then you can put that force in the equation, and then you can predict the next XYZ coordinates, the position for the atoms. What we did is we recently proposed that instead of like getting those forces and then put it in the equations, and then we can just directly predict those atomic position using these machine learning models. So it's kind of the same concept, like we applied it here. We call it the 4-dimensional because it has X, Y, Z, the coordinates of the atom, and then we have also included the time, so we call it 4D atomistic artificial intelligence model. And what we do, you can just directly predict the position, velocities, and from there you can get the force and energy. Though there are some technical challenges, and we are still working on it. Puchun is here; he's the main, the PhD student who's working on it. But like what I want to say is like the same concept can be applied to molecular dynamics. So here I want to talk about.
Arif, just a short reminder, you're running out of time.
Oh, sorry. So let me just finish it off. Okay, so here we recently released this data set here. In this data set, we have in this database, we have 8 data sets for FMO and spin boson model, and we have used 2 different kind of methods. It's already available there. You can just directly from this picture repository, you can just directly get it. And we also have this Python package for it for easy extraction, so you can easily extract the data from the database. So I will just present this MLQD later, maybe in our tutorial. So I will just come directly to the summary here. So machine learning can play the role of like a surrogate model for fast propagation of quantum dynamics. You can use it for massive kind of calculation because of its ultra fast speed. And because of in AIQD, we have these different, each time step is independent from each other. So you can do parallel calculation, and also you can predict the asymptotic state without propagation of dynamics. And you can extend these ideas, these approaches to molecular dynamics, like what I mentioned about the 4-dimensional space-time. But one thing we should remember is machine learning cannot replace the traditional methods. It just can't like make them fast. So here in acknowledgement, I will acknowledge Paulo Dral is here. We have Alexei Kananenko, we have Louis, and we have Kenneth here. We performed this comparative study with them, and also this database we also prepared in cooperation with them. So thank you very much. If you have any questions, please go ahead.
Hey, thanks a lot, Dari, for this wonderful overview. Do we have any questions from the audience? Then just unmute yourself.
Thank you, Arif, for a nice presentation. I am Kali Shankar from Germany. So I have one question regarding your FOMO complex. So could you please go back to your slide? Yes, this slide, where you have the next one. Yes, I'm wondering regarding this. You have plotted population versus time. Here, are you considering the state or just considering the chromophore involved in the reaction center?
So here, actually, we are just only considering the FMO complex. So we are not like, we are like considering that the exciton is transferred from the antenna to the FMO complex. So now how it will propagate among the chromophores of this FMO complex. So we are not considering antenna, and we are also not considering the reaction center, because on their own, they are very, very complex systems, like reaction center itself and also antenna. So here we are just studying the exciton transfer in this single complex, which is kind of a wire which connects antenna and reaction center with each other. So we are just here considering that.
So that means here the number that you define n is equal to 1 to 7. It means different chromophores that are connected by the wave. Am I right?
Here n equal to 1 means this chromophore here.
Exactly.
So we have 7 chromophores or 8 chromophores here.
Exactly. So then the population that you computed over the time, what does it mean, this population? Is it energy transfer or electron transfer or?
It's exciton. It's exciton. It's exciton. So the population, we usually use the word population, but it's actually the probability of the population in that state. So we say it's 1. So 1 means all the exciton is it's here, it's site 1. So then it's decreasing, it's transferring to this other sites or other chromophores, and it goes, because the site 3 is at the end of the reaction center here, close to the reaction center. So the whole excitons go, there are 2 possible pathways, 1, 2, 3, and there are other pathways. So it goes to site 3. So if you go here, you see, so n equal to 1 means initially at t equal to 0, it's 1. So it means the whole exciton is in site 1 on the chromophore 1. And then it's decreasing, and it's decreasing, going back, and then it's transferring to other sites. And you can see it. If you go a long time at 2.5, it's just going to 0, like you see.
Yeah. For me, it's quite very interesting, because if I figure out the height over the time, then it will give us some idea about our atomistic picture of the complex that we have studied. So it's really very interesting for me. Yeah. Thank you for your clarifying this question.
Okay, do we have some other questions from the audience? Okay, if not, then I have one. That's like, I really enjoyed your talk, but did I get this correctly? In your AIQD method, you don't have any information about the real mechanisms. You just get the results of the dynamics. Like you don't have any atomistic information.
What do you mean by mechanism?
Information on how the atoms move. So you don't use this.
Okay, I understand. The point is here, like the method that I'm using is called Hamiltonian-based method. So what you do is, this method is like how you construct. Let's talk about how you construct the Hamiltonian first for a system. So you first find out your equilibrium geometry, and then you do these atomistic calculation like dipty or other calculation maybe, and then you find the energies. The energies means the diagonal terms of the Hamiltonian. And then you also find the interaction between different sites at different atoms or different states, which is the up diagonal of the Hamiltonian. So what you do is you find out the energies which will become the diagonal elements of the Hamiltonian, and you find the interaction, which is Coulombic interaction and other van der Waals interactions. You also calculate those terms, which will become your up diagonal terms of the Hamiltonian. When you construct that Hamiltonian, use that Hamiltonian in propagate a Schrodinger equation. You can call it Schrodinger equation. And then you propagate the dynamics of it. So what we did is we already have the Hamiltonian. And then we just put it in our equation, which is a Schrodinger equation, you can say, and then we propagate the dynamics. So we are propagating the density matrix of the system, including the effects of the environment. Yeah.
Thanks. If we don't have any other questions, then I guess we move on to the tutorial session.